Okay, you must to see the presentation. So, at previous lecture, we are discuss velocity diagrams, and you make the task and you are successfully completed. So, and I hope you understand what the velocity diagram. It's really very important moment because it's contain a lot of information. It's very important for the analysis. And if you know velocity diagram, you know the blade shape. That's why it's the key moment of the design of the turbomachinery stage design process. It's the first idea. And looking to the forward, a few lectures in the future, I will explain to you what the design process of the turbomachinery stage. It is not very hard. It's really not very hard, and it's really rather easy. And you will see what the key position of the designing process of the turbomachinery. It's the creating, designing of the velocity diagram. And I will show to you in future lectures what if you know velocity diagram, you know everything about the stage. That's why the velocity diagram it's the key position, key idea for the designing process of the turbomachinery. And one second. At this slide, you see the velocity diagrams for the compressors, for the turbine. It's not important at this moment. So, how do you think? How many parameters I need to choose to describe the velocity diagrams? And by the way, to describe the working process of the turbomachinery stage. So how do you think, how many parameters I need to use to describe the velocity diagram?
7.
7. Good choice, good try. It's close to reality, it's good trying. So, okay, perfect. So it really seems what we need a lot of parameters to describe the shape of the velocity diagrams. Okay, let's try to find how many parameters we need to use. First moment, let's look carefully to the velocity diagram. One second, I will change the color. If we look carefully to the velocity diagram looks like trapezoid. It's trapezoid. That's why our aim to set the shape of the trapezoid. So at these two velocity diagrams, we make assumption what C1A equal to C2A, because in reality they could not be equal, and we set the assumption what U1 equal to U2. So let's try to find how many parameters using such assumptions we need to use to describe shape of velocity diagram, and by other words to describe shape of the trapezoid. So we need to set lower base this moment. It's the first parameter. The second parameters we need to set the value of upper base, this value. We need to set the height of the trapezoid, it's the parameter number 3. And parameter number 4, we need to set the position of the upper base relative to the lower base. So that's why if we have such assumptions, such limitation, we need to set the 4 independent variable parameters to describe the shape of the trapezoid. If we will not use this assumption, we need to add 2 additional independent variable parameters. So that's why we need to use approximately six independent variable parameters. It's close to the value 7 which you are saying before. Okay, perfect. And if we will look to the process of the design, to the design and process of the turbomachinery, we could to say what our main aim to find the combination of six independent variable parameters which are provide the best efficiency, the satisfying of all limitation and other moments. But of course, I think you understand what if you have a great number of independent variable parameters, it will be very hard to find the optimum combination. But of course, 6, 7 independent variable parameter, it's not very hard. Modern programs for mathematical optimization could to help to solve this problem for us. But in any case, for us, it will be good idea to try to reduce number of independent variable parameters. That's why let's divide all elements of velocity diagram to the value of circumferential velocity. And we are receiving dimensionless velocity diagram. All elements of these diagrams are divided by circumferential velocity. At this case, all this, the lowest base of the trapezoid will be equal to 1, and it's mean what we are remove one independent variable parameters. That's why to describe the shape of dimensionless velocity diagrams, we need only 5 as maximum independent variable parameters. So we are reducing number of independent variable parameters. What I want to say, 1 second. So a few words about this value. You see what the distance between these 2 points, it's the value delta W. If we will divide delta W to U, we need to multiply all elements of this value to circumferential velocity, and that's why at upper part of this relationship we will receive specific work, because delta W multiplying by U, it's the Euler equation, and it's specific work of the stage. And at down part of this parameter we will receive U in second degree, at degree 2. So that's why this value could be calculated like specific work divided by U in degree 2, and by other words, this value are called load coefficient or head coefficient. It's depend from the application. It's really sounds strange, but it's very often you could to say what the same physical value have the different names in the compressor and in the turbine. And head coefficient are used in the compressors, load coefficient are used in the turbine, but in reality it's the same value. At the height of the dimensionless velocity diagram described by this value, this is axial velocity divided by circumferential velocity. These values are called flow coefficient. So that's why the shape of dimensionless velocity diagram could be described by following parameters. So if we are taking the assumption what CA are constant, and circumferential velocity constant, the shape of the velocity of dimensionless velocity diagram described by upper base by this length, and these lengths are called load coefficient or flow coefficient. Well, sorry, head coefficient. So the height of the velocity diagram described by flow coefficient. And we need to only, using this assumption, we need only one parameters, one additional parameter to describe velocity diagram, and this parameter must to set the position of upper base relative lower base. Of course, we could use any value which we want. For example, we could to choose any angles which we want. But it's not very convenient because the value of angles could be changed in very wide range. That's why more physically correct, more convenient to use value degree of reaction. And if you remember, when we are discuss degree of reaction, we find such relationship, and based on this relationship, we could to find value C1U and divided by U and C2U divided by U, and this value set the position of upper base relative to the lower base. So what's the final idea here? What's the shape of the dimensionless velocity diagram in the case when you are fixed circumferential velocity and axial velocity? You need to use only three independent variable parameters to describe the shape of the velocity diagram. But shape of the velocity diagram describes the working process of the turbine. By other words, it means what if you know the velocity diagram, you know everything about the working process of the turbomachinery. That's why if you use such assumptions, you need only three independent variable parameters to describe all working process of the turbomachinery stage. If you are not use these assumptions, you need additionally two parameters which will be set the shape of the flow path. It's the parameter number 4. And the parameters which describe the meridional acceleration of the flow inside the turbomachinery stage. So that's why the final conclusion, deal this slide, what for describing of the working process of the turbomachinery, you need 3 till 5 independent variable parameters. And you're choosing these 3 or 5 parameters, and you know everything about the stage, including distribution of all parameters, including efficiency, including the shape of the blades. So here, at this slide, you could find the influence of the different important parameter to the shape of the velocity diagram. So you see, if you are increasing head coefficient, the upper base will be increased. The distance between these ears will be increased. If you are increase float coefficient, the height of your velocity diagram will be increased, and if you are reduced velocity coefficient, the height of the velocity diagram will be reduced. And the value degree of reaction set the position of upper base relative to the lower base. So if you will increase degree of reaction, as far as I remember, the upper base will be moved to the right direction, but I'm not sure. So, and at this slide shown typical range. So first we have connection between load coefficient and flow coefficient using using this equation. And here in the tables, you see the typical range of changing of the flow coefficient and head coefficient. For us, it's much interesting values for XL turbine. It's useful range for the XL turbine of the gas turbine engine, and for XL compressors. And of course, flow coefficient for XL turbo machinery, compressors and for the turbines. So that's all at this chapter. We are complete the chapter number 2. So, and we are complete about the dimensionless velocity diagram and about the main parameters which are described the working process of the turbo machinery. Do you have any questions here?
No.
Perfect. So I hope it's clear. But we will repeat this moment when we will speak about the designing process of the turbo machinery stage. So that's all about
I
the
have a
second
question.
Yes, perfect.
You said last time there is 2 models for this velocity diagram. With,
Yes.
yes, so we can't use the second model with the upper point on the same point to show the difference between height and low.
So I'm not clear understand what you mean. You mean what we have?
Yes, this first variant, we can't use this first to show.
You could to use the first variant too, but for example, at this case, when we are discuss what parameters are need to describe the working process of the turbo machinery, are more clear using variant number 2.
Yeah.
Sometimes more clear to use variant number 1 to describe some changes in the turbo machinery. Of course, for students, maybe it's not clear then at which case more convenient to use, which variant more convenient to use in different ways. But you see what at this case which we are discuss here, more convenient to use the second approach. But sometimes more useful to use first approach. I think in reality, it's not very big difference, because you are using the same inlet and outlet triangles to build the velocity diagrams, and that's why I think it's not very big difference. It's depend from what convenient for you, and sometimes it's depend from the task, which variant are more convenient for explanation. Okay?
Okay.
Perfect.
Okay.
Let's change the presentation. So we are finishing the fundamentals of the turbo machinery, and at the next chapter, in general, I'm going to repeat the second chapter, but it will be concentrated information, and we will speak about the principle of operating of the compressors and of the turbine. Of course, in the base of the XL machines, mostly. But maybe we will speak a little bit about the centrifugal turbo machinery. So that's why today I'm going to discuss principle of operating of the compressor in general. First, let's start from definition. The compressor is the device at which we are realizing continuous compression of the working fluid, and compression are provided because we are supplying mechanical energy to the flow using special elements which we are called the blades. So, at this definition, we need to pay attention what this type of the compressor, the XL compressor and centrifugal compressor, have the special feature. Then one of the special feature of such type of the compressor, what we are using continuous compression using this type of the compression compressor device. So it's the first idea. The second idea, what we are supplying mechanical work, and what the energy exchange take place because we are using special profiled elements which are called blades. At the next step, I will explain why the pressure will be increased in the compressor. So here at this slide, you see some example of the compressors, but in any case, it will be it's the XL multi-stage compressors. For example, this is a high pressure compressor of why it doesn't work, CFM56. Looks strange. CFM56. Sorry, 56 till 7. This is Russian engine AE25 low pressure compressor. This is Rolls-Royce Trent. I don't remember what the number. This is intermediate pressure compressor, and this is industrial gas turbine power unit. I don't know the real name of this engine. So, few words about the compressor. The compressor could be classified by number of stages. Single stage and multi-stage compressor, and compressors could be classified by the direction of the moving of the working fluid. The compressor could be axial and could be centrifugal. As we had discussed in previous lectures, centripetal compressor are not allowed to receive high pressure ratio. That's why it doesn't use in real practice. So, and in the pictures you are see the examples of the single stage centrifugal compressor for the charging of the piston engine and multi-stage axial compressor. So, I refresh the information what the typical stage of axial compressor consists from two main elements: rotor wheel, and it's set at the first position, and guide vane, which are set after the rotor wheel. So typical compressor stage consists from two blade row. First of them will be moving blade row, and it will be rotor wheel. Sometimes at the first stages and at the separate stages, you could find additional non-moving blade row, which called inlet guide vane. The cross section between the blade rows have the numbers, and number 1 corresponding to the cross section at the inlet of the rotor wheel, number 2 corresponding to the cross section at the outlet of the rotor wheel, section number 3 at the outlet of guide vane, and section number 0 at the inlet of the guide, at the inlet of inlet guide vane. The requirements for the modern compressor very typical for every aerospace application. The compressor must have high efficiency, must have good reliability, good resource, must to have minimum dimensions and weight, must be have low manufacturing cost, and will be technological and easy to use. You see what these requirements are very typical for every aerospace application. Maybe some special requirements for compressor. The blade compressor must have wide range of the stable work. It's really very important for the turbomachinery compressor stage, because you will see in future lectures what it's have rather narrow range of stable operating, and it's really big problem for the axial and centrifugal compressor, especially for the axial compressors. And that's why we have requirements to provide wide range of stable work. So it's short brief about the compressors from previous lectures. Let's discuss the principle of operating of stage of the of compressor stage. So now we will speak about the principle of operating of compressor stage, and we will explain why the pressure are increased in the compressor stage. So you will see in reality it's rather easy. So we will start from the Bernoulli equation. We will write the Bernoulli equation for the rotor wheel. So we know what for the operating of the compressor we need to supply mechanical energy from outside, and we are rotating the rotor of the compressor, and during rotating we are supplying mechanical energy to the compressor. And based to this Bernoulli equation, we could to say what all mechanical energy which we are spent which we are supplied to the compressor are spent to three directions. First, it's spent to increasing of potential energy. It's spent for increasing of the pressure, by other words. It's spent to increase in kinetic energy in the compressor, and it's spent to overcome of hydraulical losses in the flow path. So the specific work are spent to the three ways. In the gas turbine engine, the main aim of the compressor increasing pressure. That's why we need to provide what the biggest part of supplying mechanical energy must be converted to the increasing of the pressure. That's why we need to not change the kinetic energy, and we need to reduce hydraulical losses. It's the first idea of the working process. For the second idea, for the second key point, for the second idea, we need to write energy equation in mechanical form in relative motion for the compressor. It looks like at this picture, and based to this equation, we could to say what the pressure in the compressor increase due to we have working fluid movement in the field of inertia forces. It's the first term. And because we are decelerating flow in relative motion. So by other words, to increase in pressure, we need to organize movement of the working fluid in the fields of action of centrifugal forces, and we need to break the flow in relative motion. These two equations, it's the key point of the compressor principle of operating. And it's really enough to describe why the increase in pressure. Let's imagine you are working in some company which produce compressor, and you are engineer, you are chief, you are boss, and you need to explain to the workers from Egypt how to create the shape of the blades to receive the compressor. And if you say to guys with the low level of education, let's provide the, how to say, conversion of mechanical energy to kinetic energy. They doesn't understand you. You need to say how to realize this moment in real construction, how to realize the real construction of the compressor to provide movement of working fluid in the field of centrifugal forces, how to organize the construction, how to create construction to organize flow deceleration in relative motion. That's why let's try to find, implement this knowledge in real design, in real construction. So first, let's start from the first term of energy equation. To increase pressure, strange. Sorry. To increase pressure, this term must be more than zero. Yes, and it's mean what we need to provide what U2 circumferential velocity at the outlet of the turbomachinery, at the outlet of the rotor must be more than circumferential velocity in the inlet of rotor. How we could organize it? Very easy. You know that the circumferential velocity depends only from two things, from the radius and from angular velocity. Of course, angular velocity the same for the inlet and for the outlet. That's why we have only one source on influence to the circumferential velocity, radius. And that's why to organize action of circumferential velocity to the flow, we need to organize the change of the radius. We need to organize what the R2 will be more than R1. And how to implement it, how to realize it in the construction. You need to organize the inlet in the lower radius and outlet at the upper radius. And that's why we comes to the scheme of centrifugal compressor. So, if you will create the compressor such what the inlet will be in the lower radius and outlet will be at the upper radius, you will receive the action of centrifugal forces on increasing of the pressure. It's the first idea. The second idea, let's discuss if you want to pressure increase, you need to organize to make what the W1 will be more than W2. It's mean what we need decelerate, we need to break the flow in relative motion. And the next question, how to break the flow, how to organize flow deceleration. Very, very easy. You need to create the divergent shape of the channel between the blades. By other words, you need to create diffuser shape of the blade channel. And it's very interesting question how to explain to the workers with a low level of education how to create the diffuser channel. It's very easy. If you create the angle at the inlet lower than angle at the outlet, you will receive the divergent channel between the blades. And that's why using this relationship, you could explain to your workers how to create the compressor blades. Of course, in reality, you will set the real values of angles. So you see, it's very easy to organize in the construction pressure ratio. You need to put the flow inside the compressor in the lower radius and put it out at upper radius. And the flow channel between the blades must be divergent, must be diffuser, must have diffuser shape. At this case, you will receive the pressure ratio in the rotor wheel. So let's look to the velocity triangles in the rotor wheel. In the inlet of the rotor wheel, the particle of the air which comes into the rotor take place in the two actions, in two motions. From one hand, sorry, 1 second. The flows come into the rotor wheel with the absolute velocity c1, with the angle alpha 2. At the leading cage of the rotor, it's begin to take place these two motion, these two movement. From one hand, the particle moves relative the rotor blades with the relative velocity W1 with the angle beta 1. And from other hand, the particle rotates with the rotor with the circumferential velocity U1. We usually make the beta 1 blade angle equal to beta 1 to reduce the losses, and that's why it's give to us shape of the blades in the inlet part. So the flow leaves rotor wheel with the velocity W2, and because we are using diffuser shape of the channel between the blades, the value of W2 will be lower than the W1. Let's assume vector W2 is the vector of circumferential velocity at the outlet. And finally, we will receive the absolute velocity at the outlet of the rotor. So you see what the absolute velocity C2 will be increased at the outlet of the rotor, and it's take place because we are supplying work. So in reality, it's very interesting moment, and it's really strange moment, because we are making diffuser shape of the blades, and we are breaking the flow in relative motion, but velocity in absolute motion will be increased. In my opinion, it looks strange, but it's really so, because in the rotor wheel we are supplying mechanical work, and that's why absolute velocity will be increased. And you see what, looking to the forward, C2 is the velocity with which we are into the guide vane, and that's why we will choose, we will orient stator blades regarding to the vector C. So the next moment, I pay your attention what the absolute velocity I increase in the rotor wheel. And if we will look to the Bernoulli equation, it means what the second term will be more than 0. And it means what we are not convert on all mechanical energy which we are spent in the which we are supply in the compressor into the pressure ratio. So it means what we are spent some quantity of energy to increasing of the kinetic energy. But our main aim to increasing pressure. That's why we not need high velocity at the outlet of the rotor wheel. The high velocity at the outlet of the rotor wheel indicate what we are transfer of the mechanical energy into the kinetic energy, but we need to receive potential energy. That's why we need that's why finally we are not receive sufficient pressure ratio, and we need to convert exceed kinetic energy into the increasing of the pressure, and we are using guide vane to increase pressure. So it's really very important moment. We are find the function of the guide vane. The function of the guide vane not only guide. It's typical answer of the students. What the function of the guide vane? The guide vane guide the flow to the rotor wheel. Of course, it's true, but it's not the main function of the guide vane. Main function of the guide vane to convert exceed kinetic energy at the outlet of the rotor to the pressure, to the potential energy of the flow, and it's finally help to us to increase static pressure. So what's the main aim of the guide vane? So what else? Let's very fast look to the forces which impact to the blades in the rotor wheel. So in the rotor wheel, at the pressure side, pressure more than at the suction side. That's why we have assumed force which direct like in the picture, and we could to divide this force to two projections: axial projection and circumferential projection. And the same force are acting from the blades to the flow. The force R, it's the force with which blades pushing to the flow. And this force could be divided to the two projection, RU, in circumferential projection RU, and axial projection RA. So, and if we look carefully to the forces, we will find what we want to move blades to the right direction, but we have force PU, which are direct to the opposite direction, and this force break the movement of the rotor wheel. And that's why we need to supply mechanical energy to rotate the rotor wheel. And finally, we could to say what the force RU, it's the force which are supply mechanical work to the flow. And force RA push the air through the compressor and provide the movement of the fluid from the region of the low pressure to the region of the high pressure. That's why we could to find the function of the rotor wheel. The rotor wheel provides three main functions. It supply work to the flow using force RU. It's push the working fluid through the compressor using force RA, and of course increase pressure. And the last idea deal with the working process of the compressor. Because we are increasing pressure, this density will be increased, and based to the continuity equation, with the approximately same axial velocity at the inlet and at the outlet of the compressor, we need to reduce cross-section area, we need to reduce blade heights to the outlet. So, what blade heights, it is not the reason, it is It is not the, so I forgot the word. Oh, it is not the reason of increasing pressure. It's the conclusion from increasing density. First, you are increasing pressure. The second, you need to reduce the blade height. So I think that's all. So, of course, maybe my explanation is not very good, especially on English, but I want to show to you what the principle of operating of the compressor very simple. You are based to this equation, and you based to this equation you are saying what the pressure increase because what for increasing pressure we need to provide movement of the working fluid in the field of centrifugal forces and decelerate flow in relative motion. And at future step you are explain how you will realize it in real construction. You are organize moving of the working fluid from lower radius to the upper radius, and you organize breaking of the flow using diffuser channel. That's all. And after that you say what then you are supplying mechanical energy, you are increase absolute velocity at the outlet of rotor, and it's mean what you are transfer part of your mechanical work into the kinetic energy. But it is not our main aim to increase in kinetic energy. Our main aim to increase in pressure, and that's why we need to convert exceed kinetic energy to the potential energy of pressure. And that's why we are breaking the flow in the guide vane after the rotor wheel to convert the velocity to the pressure. And that's why we need to use guide vane. And after that, we are saying what the main function of the rotor wheel supplying mechanical work, push the working fluid through the compressor and increase pressure. And at the last idea, we explain why the blade height will be reduced from inlet to the outlet. So that's all about the principle of operating. So, guys, it's important. It's important part. I think it's the most important information. One of the most important information at this course. That's why. I need what you understand this part. So, do you have any questions?
Yes, for me it's not clear yet the main goal of the guide vane.
Okay. So,
to guide the flow, yes, but the main goal, no, I don't understand.
Main goal convert the kinetic energy to the pressure. So, because you are supplying mechanical work, you are receive high absolute velocity at the outlet of the rotor.
Yes.
You are receive very high C2. It means you have high kinetic energy. You need to convert it to the pressure. You need to convert velocity to the pressure. How you could to organize it? You need to break the flow.
Okay, yeah.
And that's why after the rotor, you put the non-moving channel, non-moving diffuser channel. This is diffuser channel.
Yes.
And you are breaking the flow, and finally you are reducing velocity. C3 will be lower than C2. And finally, it will be leads to increasing pressure. And that's why the main aim of the guide vane to convert big velocity to the pressure.
Yes, okay.
It's okay?
But what is breaking the flow? the fact that it's not moving, or the fact that the blades are in the opposite
Braking,
sense?
braking, I mean reducing velocity.
Yes. Yes.
So of course we couldn't break the flow till zero.
No.
Because it's important. Oh, sorry, impossible.
Yes. But the brake, the little brake is due to the non-moving blades, or the sense, or the opposite sense of the blades between a rotor wheel and a guide vane. If you have non-moving blades, but in the other sense, like the rotor wheel.
So how to explain? So in non-moving blades, the pressure and velocity change in the opposite direction. Because do you remember we are discussing Bernoulli equation? What if you are not supplying mechanical energy into the flow, it means non-moving channel. The velocity and density will be changed opposite. And if you and if in non-moving channel you will be reduced speed, you will be increased pressure. But we need it. And that's why we put non-moving channel, because we not need supply mechanical work at this moment.
Okay.
Okay?
Yeah.
Perfect. So. Okay, let's continue to discuss the working process of the compressor. I will try to do it fast, but it's not a lot of material. So I want to discuss with you how the main parameters are changed along the flow path of the compressor. So I want to discuss how the main parameters like pressure, density, velocity are changed in the rotor wheel and the guide vane. So we could to explain it mostly based to the principle of operating. So as you remember, in the rotor wheel, we are reduce velocity, reduce relative velocity, because we are organizing the diffuser channel. That's why the change of relative velocity will be relative velocity will be reduced in the rotor wheel. Absolute velocity in the rotor wheel will be increased because we are supplying mechanical work. In the guide vane, we are organizing the diffuser channel, and that's why we are reducing the absolute velocity in the guide vane, and absolute velocity in guide vane are reduced. And you see what the changing of absolute velocity in the compressor stage have the maximum. At first moment we are increasing velocity, and after that we are reducing velocity. And very often we are reducing approximately to the same value of velocity. It's really a typical design practice. Then the inlet velocity approximately equal to the outlet velocity. So, but you see, this explanation comes from the principle of operating. So maybe returning back to the previous discussion, maybe it's not clear, but in the rotor wheel, we are realizing braking, reducing velocity in relative motion. And in guide vane, we are organizing reducing velocity in absolute motion. Maybe this moment are not very clear. So, and because we are breaking the flow in the rotor wheel, we are achieving increasing of the static pressure. And because we are reducing reducing absolute velocity in the guide vane, the static pressure continue to increase in the guide vane. So these graphs are explained by the principle of operating. About the total parameters and the temperature. They are explained based on the energy equation. So if we will write energy equation for the compressor, you will see in the compressor we are supplying mechanical work. That's why total enthalpy and of course total temperature will be increased, and static enthalpy and static temperature will be increased. In the guide vane, static enthalpy will be increased based on this equation, and total enthalpy will be not changed because we are not supplying mechanical work, and it's mean what the total temperature will be constant. And approximately the same explanation deal with the total pressure. As you remember, I hope, total pressure change only in the case when we are supplying mechanical energy, and that's why total pressure will be increasing the rotor wheel and must be constant in the guide vane. But because we have losses, in reality, total pressure will be a little bit reduced in the guide vane. The value of reducing not so big, I think in most cases not more than 5%. So it's the very short explanation deal with such graphs. And the last idea for today, the main parameters which are described the working process of the compressor, it's two parameters. First, pressure ratio, it's the relationship between pressure at the outlet of compressor and the pressure at the inlet of the compressor. And this value shows how many times the pressure in the compressors are increased. It's a very interesting moment because every students deal with the turbomachinery, deal with the gas turbine engine, know the equation, know this formula, but I'm very wondered what most of the students couldn't explain the physical mention of this formula. And the next important parameter is the efficiency. But before we will discuss efficiency, term efficiency of the compressor, let's try to understand the energy balance, energy conservation in the compressor stage. So, how the energy are converted compressor stage? We are supplying some mechanical work from source of energy. Usually we are using the turbine, but in reality it could any source which you have. It could be a piston engine, it could be electrical engine. It's not important at this case, but for the gas turbine engine, it's the turbine. So we are supply this energy from source of energy, and this energy are called expanded head. And we begin to transfer this energy to the blades. And at this way, we have some losses. First losses, we lose some energy in the radial gap with the leakages. And we lose some energy to overcome friction on the surface of the because disk surrounded by gases, and we have boundary layers, and we have friction, which try to reduce rotational speed of the rotor, and we need to spend some energy to overcome friction on the disk surface. All energy which we are not spent to overcome losses, we are using our blades transfer to the flow. And this energy could be calculated using Euler equation. So we are supplying this energy from the blades to the flow. Of course, not all the energy are spent to the increase in pressure. Of course, we are spent some energy to overcome hydraulical losses in the blade channels. And I remember to you what this moment leads to increasing of the temperature of the flow, because you know all losses finally to the heat and finally leads to increasing temperature of the working fluid. But in the compressor, it leads what we need to add additional work to compress more heated gas. So I refresh to you what we are paying twice for the losses in the compressor. From one hand, we are spend some energy for overcome hydraulical losses. It's leads to increase in temperature, and that's why we need to add additional energy to compress more heated gas. So, and all energy which we are not spent to overcome any losses, we are spent to create compression. And specific work of ideal compression could be calculated using famous equation. So this is steps of energy exchange, energy transfer in the compressor stage. You see what we are transfer energy from source of energy to the blades, and after that from the blades to the flow. And based to these steps, we could to explain what's mean efficiency of the compressor in common. The efficiency of the compressor, it's the relationship between the useful work and expanded supplying work. In the compressor, it's very easy to explain what work are useful and what work are expanded. In the what we are finally receiving in the compressor. In the compressor, we are receive compressed air. That's why specific work of ideal compression, it will be useful work in the compressor. And what we are spent to create compression process in the compressor. We are supplying energy from outside. And that's why the energy which we are supplying from the source of energy, it will be expanded work in the compressor. So that's all about the compressor. So today's lecture will be very important because I think especially at the first part of my course, that you need to understand two main things: the principle of operating of the compressor and principle of operating of the turbine. That's why today I'm trying to summarize all information, deal with the compressor from the second chapter, and formulate to create the explanation of the principle of operating of the compressor and explain how the parameters are changed along the flow path of the compressor, and explain compressor efficiency. So, do you have any questions, guys?
Yes.
Okay.
I don't understand why we need additional energy to compress the heated gas.
Okay. So, if you look to this equation, you see what the specific work which you are spent for the compression depend from the temperature. And how to say, finally, all losses are converted to the heat. And finally, the temperature of the real process higher than the temperature of ideal process. And that's why in real process, to receive same pressure ratio, you need to to add additional specific work because the temperature of real flow are higher than in ideal case. Okay?
Okay, yes. And how can we quantify the evolution of temperature due to losses?
It's very interesting question. It's really very interesting question. It's a really very interesting question. So I think in reality, we are not calculated it. In reality, for us, it's much interesting to calculate efficiency, and we are calculating efficiency using some loss models. Loss models, it's the empirical formulas which are received based to the some experimental data. I think so. And of course, if you make CFD calculation, you could to receive this temperature in CFD calculation. It will be more accurate, of course.
Okay, thank you.
Okay, so guys, if you have no any other questions, we will be finished today.